We've learned already what the dot product is. It's a way to multiply vectors that gives us a single number, that scalar value. We've also seen how it measures how much one vector goes in the direction of another. But here's the real power of the dot product. It lets us answer real-world questions, not just numbers for the sake of numbers. I'm talking about actual decisions in physics, engineering, and computer science. For example, if we want to know if two forces are working together or against each other, that's the dot product. We want to know if two directions are perpendicular, dot product again. Want to calculate how much work is being done by a force, dot product. Want to project one motion onto another path? You guessed it, it's the dot product. What we're going to do today is take the simple formula we already know, and that formula is A dot B is equal to the magnitude of vector A times the magnitude of vector B, but it's vector B in the direction of A, so it's vector B times cosine theta. I'm going to clean that up a little bit. Vector B cos theta. Okay, so we're going to use it like a tool to solve problems in two-dimensional space, 2-space, or 2D. We're going to look at work done by a force again. We're going to look at the angle between vectors this time. We're going to look at orthogonality, and that's really just how do we know, it's a fancy word for perpendicular, so how do we know if two things are perpendicular, and we actually have already looked at this. And then we're going to talk about a big idea in this unit is projections, and it really is one of the coolest ideas in vector math. So the goal for today is simple. See the dot product is not just as math. See it not just as math, but as a lens for understanding how vectors interact in the world around us. Okay, so now let's talk about this idea of a projection. And you can think of a vector projection like a shadow. So the vertical arrows in this picture, and I apologize that these pictures are not fantastic. I pulled these from the textbook, and for some reason, the PDF that I have of the textbook is a little blurry for this section. I'm not really sure why. So we can think of a projection, like I said, as a shadow. If you think of there's a light source up here, and these are light rays coming down. So we can think about a projection as being this reflection, and the vertical arrows in the diagram represent a light from above. And so this projection of V onto U is the shadow that V is going to cast onto U. So we can find that the projection is formed by dropping a perpendicular line down from the tip of the vector that's being projected and creating this new piece of vector that follows the same direction as the other vector. Now we would write this as the projection of vector V onto vector U. So the vector that's being projected is up here at the top, and it's being projected onto the other vector on the bottom. So that's projection V onto projection or vector U. So the projection of vector V onto vector U. So that's if the angle is between 0 and 90 degrees. So if the angle between the two vectors is less than 90 degrees, then the projection of V onto U will be, I'm just going to start that one over again. If the angle between V and U is less than 90 degrees, then the projection of V onto U is the vector component of U in the same direction as B. So if this is between 0 and 90 degrees, same direction. So the projection will be in the same direction as the other vector that it's being projected onto. Now, if the angle between the two vectors is between 90 and 180 degrees, so if we're between 90 and 180 degrees, then this projection, the projection of V onto U, is going to be negative. It's going to be in the opposite direction. So it's opposite direction. It's in the opposite direction. Now, what happens if we have them at 90 degrees? So if vector v is perpendicular to vector u, then v doesn't cast any shadow onto u at all. So we can say that if if v is perpendicular to vector u, or vice versa, it doesn't really matter. It won't cast a shadow. So if theta equals 90 degrees, then we can say that the projection of v onto u is equal to 0. And this is actually why the dot product of v dot u would be 0 for perpendicular lines. And we've seen a couple of examples of that now where that dot product is 0. So how can we use this dot product to determine the angle between two vectors? Well, in order to do that, we can actually rearrange the dot product formula, that a dot b equals the magnitude of a times the magnitude of b cos theta, to isolate for cos theta. And when we do that and we rearrange, we get cos theta is equal to the dot product of a dot b all over the magnitude of vector a times the magnitude of vector b. So when can we use this formula to solve for an angle, the angle between vectors? Well, this can only be used when we can determine the magnitude of each vector, and we can only do that if we have algebraic vectors. So I think the best way for us to figure this out is to go ahead and do a couple of examples. So let's look at this first one, example A. We're going to determine the angle between each pair of vectors. So I have vector G that's at 5, 1. And remember, when we've got these square brackets like this, what this really means is that this is starting at the origin, and the tip of vector G is going to be at 5, 1. Then I have vector H, which similarly starts at the origin and has its tip at -3, 8. So if we wanted to think about what this looks like, we can always draw it out. So here's our Cartesian plane. My first vector G starts at the origin and has its tip at 5, 1. And I'm just going to estimate out 5 and up 1. So we're going to estimate that it's right there. And just to remind us, I'm going to put that there. And then we have a second vector H. So this is vector G. Now we have a second vector H, and that's at -3, 8. So we're going to come over here, -3 and up to 8. So here's my vector G at -3, 8. Okay, so that's what this actually looks like if we were to draw it out. What we're trying to find is the angle that's in between them. And I've drawn it to look a little bit like 90 degrees, but we're going to do some math just to see if that's actually what's happening. So let's use our formula. So we know that the cosine of the angle is going to be equal to, now in this case, we've got H and G. Here's what I found. Okay. Sorry, my iPad was just doing something weird. So we have vector G and vector H. Just realized I labeled that one wrong. And we want to find the angles. So we are going to take the dot product, G dot H on the top, all over the magnitude of G times the magnitude of vector H. Now, we know how to find all of these things. Just as a reminder, the dot product for algebraic vectors tells me that my dot product of any two vectors, so in this case it's G dot H, will just be equal to my x component of the G, vector G, times the x component of vector H, plus the y components of vector G times the y components of vector H. So we can go ahead and put that in on the top. So we have my x component of G is 5. So we have 5 times the x component of H is -3, plus my x component, my y component of g, which is 1, times my y component of h, which is 8. Now, we need to know the magnitudes of both of these vectors. And remember, we can do that using the Pythagorean theorem. So if I want to find the magnitude of both of them, I'm going to use my Pythagorean theorem. And let's say we're starting with the magnitude of g. So we know that g is going to be made up of 5 squared plus 1 squared, the square root of 5 squared plus 1 squared. We're just finding the hypotenuse. So we can say that that is equal to gx squared plus gy squared. And if we want to just find g, then we take the square root of that, gx squared plus gy squared. So we're going to go ahead and we're going to put that down on the bottom. So we have to do that both for g and h. So for g, we get the square root of 5 squared plus 1 squared, and we're going to multiply that by doing the same thing by the magnitude of vector h, which is negative 3, 8. So we have negative 3 squared plus 8 squared. When we do all the math on that, 5 times negative 3 plus 1 times 8 gives us a value of negative 7 on the top, and we end up with 5 squared plus 1 squared gives me the square root of 26, and negative 3 squared becomes 9, plus 8 squared gives me a root of 73. Okay, so now in order to find that angle, I'm going to do the inverse. So theta will equal the inverse of cos of this ratio of negative 7 over root 26 root 73. And that's going to give us an angle approximately equal to 99.2 degrees. Okay, so that's the angle in between them, is 99.2 degrees. Now let's look at another example. So now we have vector A that has its tip at negative 3, 6, and vector B that has its tip at 4, 2. Again, I'm going to draw it out just so we can look at it and what it's going to look like. So vector A is at negative 3, 6. So negative 3 and up 6. So here is negative 3, 6. This is vector A. Vector B is at 4 and up 2. So there is vector B at 4, 2. So we're going to follow this exact same process. And actually, you can pause the video if you want and give it a try and see what you come up with. Come back once you've done it and check your answer. So we are finding cosine of our angle. It is now equal to the dot product of vector A and vector B all over the magnitude of A times the magnitude of B. Okay, let's start filling in some numbers here. So we know the dot product is our 2x values multiplied together plus our 2y values. So we have negative 3 times 4 plus my 2y values, so 6 times 2, all over the magnitude of those two vectors multiplied together. So we have the magnitude of A will be negative 3 squared plus 6 squared times the magnitude of B, which will be 4 squared plus 2 squared. So cosine of theta is going to be equal to, negative 3 times 4 is negative 12, and 6 times 2 is also 12. So our value on the top is 0. On the bottom, we end up with the square root of 45 times the square root of 20. But at this point, it doesn't really matter because cosine of theta is equal to 0. 0 divided by anything is just 0. Now, what do we know about the value of cosine, the angle at 0? Well, the angle for cosine at 0 is 90 degrees. So let's go back and let's think about this a little bit. So I want to point out just a few properties of dot product that could have tipped us off to what our answers were going to be. So remember, the dot product is 0 when the vectors are perpendicular to each other. And we can see here that our dot product, so we would have A dot B is equal to 0. Therefore, the theta, it's equal to 90 degrees. They are perpendicular to each other or orthogonal. So if you're trying to prove that two vectors are perpendicular to each other, then know that if we are doing the dot product of those two vectors, it will equal 0. Now, the other property I want to point out is that the dot product is negative when the angle between the two vectors is between 90 degrees and 180. So if we go back here and we look at example A, we can see that we actually will have a negative value. So we can know without doing any math at all that this will be between 0 and 90 degrees because the dot product of G dot H is going to be negative. And I think that, well, I don't know, a cosine in that quadrant is negative when it's greater than 90 degrees, between 90 and 180. So I think that pulling on that little bit of functions knowledge, I think that that makes sense. Okay, so now let's talk about this idea of a projection. And you can think of a vector projection like a shadow. So the vertical arrows in this picture, and I apologize that these pictures are not fantastic. I pulled these from the textbook, and for some reason, the PDF that I have of the textbook is a little blurry for this section. I'm not really sure why. So we can think of a projection, like I said, as a shadow. If you think of there's a light source up here, and these are light rays coming down. So we can think about a projection as being this reflection, and the vertical arrows in the diagram represent a light from above. And so this projection of V onto U is the shadow that V is going to cast onto U. So we can find that the projection is formed by dropping a perpendicular line down from the tip of the vector that's being projected and creating this new piece of vector that follows the same direction as the other vector. Now we would write this as the projection of vector V onto vector U. So the vector that's being projected is up here at the top, and it's being projected onto the other vector on the bottom. So that's projection V onto projection or vector U. So the projection of vector V onto vector U. So that's if the angle is between 0 and 90 degrees. So if the angle between the two vectors is less than 90 degrees, then the projection of V onto U will be, I'm just going to start that one over again. If the angle between V and U is less than 90 degrees, then the projection of V onto U is the vector component of U in the same direction as B. So if this is between 0 and 90 degrees, same direction. So the projection will be in the same direction as the other vector that it's being projected onto. Now, if the angle between the two vectors is between 90 and 180 degrees, so if we're between 90 and 180 degrees, then this projection, the projection of V onto U, is going to be negative. It's going to be in the opposite direction. So it's opposite direction. It's in the opposite direction. Now, what happens if we have them at 90 degrees? So if vector V is perpendicular to vector U, then V doesn't cast any shadow onto U at all. So we can say that if if V is perpendicular to vector U, or vice versa, it doesn't really matter. It won't cast a shadow. So if theta equals 90 degrees, then we can say that the projection of v onto u is equal to 0. And this is actually why the dot product of v dot u would be 0 for perpendicular lines. And we've seen a couple of examples of that now where that dot product is 0. Okay, so what can we do with this dot product and this idea of projection? Well, if we know the formulas for calculating this projection, how much of one vector is going in the same direction as the other, then we can use that to determine the magnitude and the direction of the vector projections. Really, we can relate it to A dot B. So let's think about what we have going on here. So we know, well, I'm just going to give you the formulas. So if I have two vectors, I have vector A is projecting onto vector B, and I want to determine what the magnitude and direction of this vector is. Well, I'm going to take the dot product. I'm going to divide that by the magnitude of the other vector. And now that's my magnitude. This right here gives me the magnitude of my vector, but I need a direction because a vector, remember, has both magnitude and direction. And how I'm going to do that is by either relating it to our unit vector, and that unit vector is the unit vector for the one that's being projected onto, or I can relate it back to just the actual coordinates of that vector that's being projected onto. So we could think of it as the projection of A onto B could then be equal to A dot B. Now, if we've got the magnitude on the bottom and we're just relating it to one single vector, then we end up with B dot B on the bottom because we're relating it to that vector. And then that will be multiplied for the direction by our coordinates for that algebraic vector. So let's apply this. Your textbook goes into a little bit more explanation, than what I've done there, but I think for now this is good enough, and I think when you see it in practice you'll understand. So let's take a look at an example. So I want to do this example here. If I can find my piece of paper that I have it written on. There it is. Okay. So we want to determine the projection here of the projection of vector D onto C. So we would write that. We want to know the projection of vector D onto vector C. And we want to know the magnitude of that. So that's really what we're finding. So let's figure out, first of all, which one of these is which. So I know vector D starts at the origin and has a tip at 2, -3. So that's going to be this one here. Here's my vector D. There's the tip of it at 2, -3. And vector C then by default has to be the other one. But if we take a look, we see that it is actually at 1, 4. So let's use our formula. So the projection of D onto C. If we wanted to think about what this would look like, we know that this angle is greater than 90 degrees. So we would extend this vector out to get an idea of what it would look like. We're going to drop the perpendicular to make 90 degrees. And now this right here is going to be my projection. So that's actually what we're finding. You can kind of think of it like a resultant vector a little bit. Not really, but a little bit. Okay, so let's pick up our formula here. So the projection of D on C will be D dot C, so the dot product of DC, all over the vector that's being projected onto, so C dot C. Now we need a direction, and we're going to relate that actually to the vector C that's being projected onto. So this equals, so to get the dot product, remember it's the two x values multiplied together plus the two y values. So we have 2 times 1 plus negative 3 times 4 on the top. Now, c times c dot c. So now I'm just using this vector, and if I have the two x values multiplied together, that's just 1 squared. And then my two y values multiplied together is just 4 squared. And we're not going to forget about that vector c. Now I'm going to use just the tip of it to give us a direction, and that's 1, 4. Okay, hopefully you can see maybe where I'm starting to go with this. So let's do a little bit of math. So on the top, I have 2 plus negative 12. So that gives me negative 10 on the top. 1 squared plus 4 squared is just equal to 16. And now here's this is in relation to 1, 4. So now we can distribute this in to get the actual value of the tip of this projection. So just like we would with multiplication around a bracket. So negative 10 over 16 times 1 is just negative 10 over 16. And then 4 times negative 10 is negative 40 over 16. And that's going to give us our coordinates for the tip of that vector. So we have both the magnitude and now we have the direction. Okay, I highly recommend taking a look at the textbook section for this one and going through some of those examples. There's not a lot of homework today. So page 384, 4A, and 5, we're going to start into the world of 3D vectors next. And really, that's just going to build on what we've already done, but now just adding that third dimension. If you have any questions, feel free to shoot me an email.